Hello, welcome to the video. Uh, Looking at a new chapter. Uh, Section 9.1 is where we're going to start, and 9.1 is focusing on properties of radicals. So, anytime you hear the term a radical, that is where you're looking at the root of a value, whether that's square root, cube root, fourth root. The list goes on. In this particular section, we'll focus more on square roots and cube roots and how we are going to solve those particular problems for whatever situation that they give us. So, one of the main things that we have to kind of get an idea of, especially if we're looking at cube root and square root values, is we have to be able to identify perfect square numbers and perfect cube numbers. So, for instance, to kind of make a list, like, so if I was to make a list of the perfect square numbers, let's say put perfect square numbers, these are the values that if you, once you square them, the results, or if you took the square root of these numbers, the results are nice, clean values. So the very first one's 1 because 1 squared is 1. If I took the square root of 1, it gets me 1. If I put 2 squared, that's going to give me 4. So the next perfect square number is 4. 3 squared is 9, so 9's a perfect square number. If I put 4 squared here, that's 16. 5 squared, that's 25, and so on and so forth. So I would say if you try to make a list of these values so you can be able to easily identify what these perfect square numbers are, then it's going to help us in the long run when it comes to simplifying. If we have perfect cube numbers, this is now you got 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. And again, this list can go on, but this is just a way for you to start it. So 1 cubed is 1, 2 cubed is 8 because it's 2 times 2 times 2, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. All right. And you can make the same list for that if it's, fourth root values or fifth root values and stuff like that. Okay. So, what is going to help us in simplifying is be able to look at the product property and quotient properties of square roots, not just square roots, but any radical expression. So, but in this case, they're looking at square roots. So what they are saying is this, is if I had, let's say, because 9, what is 9 times 5? 9 times 5 is 45. So if you had the square root of 45 as a problem, if you were to punch that into your calculator, square root of 45, you get something about, in a decimal form, 6.7, we'll say. The problem is when you are asked to simplify, we don't want decimals because we don't want approximations, we want exact values. So in order for us to get exact values, what we have to do is break up this 45 into um, two products. All right. More specifically, the two products have to be this. One of the values has to be a perfect square number because we're dealing with square roots. That's why you have the 9 there. 9 is that perfect square number, and then the other number multiplied by that perfect square number gives me 45. Then what you can do is split it up into two separate radicals or two separate square roots. Square root of 9 times by the square root of 5. Well, what this does is this square root of 9 gets it out of the radical, and finally it's simplified as 3 times it by the square root of 5. That's the answer that we are looking for in these types of situations. So what we can do is break these up into series of products, and then eventually we can simplify them. All right, and we're going to show some examples and how these are simplified. So if you look at these two examples here, this first one here is the square root of 1 108. If I took the square root of 108, it's not a perfect square number, but it is the product of two values in which one of them is a perfect square number, and that is 36 is my perfect square number because the square root of 36 is 6, but what I have left over is a square root of 3, so this is my simplified expression. Now, in a situation like in example B here, we have not only numerical values, but we have variables. So what you are going to do in this particular instance is, well, 9's already a perfect square number, so I don't have to do anything with that. But if you look at the variable, it's this. What you're going to do is break this up into a series of, basically because it's square root, you're going to do an even exponent, which in this case is going to be x to the second, and then you have whatever's left over, which is x to the first. If this was already an even number, you wouldn't have to deal with anything. So all what happens here is it gets broken up into the square root of 9 times it by the square root of x squared times by the square root of x. The square root of 9 and the square root of x squared are two values that are going to be placed on the outside of the radical, outside of the square root. Square root of 9 is 3, and the square root of x squared is simply x because these two cancel each other. If it's anything that's larger than x squared, so let's say it was the square root of x to the sixth, we'll say, which six exponents an even number. All you're going to do to get it out of the square root is divided by 2. So the square root of x to the sixth is x to the third power without the radical attached to it. All right, means the same thing. All right, so now let's take a look at these examples here and see if we can simplify them. So here I have the square root of 24. Square root of 24 is not a perfect square number, so what I have to do is break this up. And the first thing that I think of is what? 4 times 6. 4 times 6 gives me 24. My perfect square number is right here. If you remember from the first page how I made that list, 2 squared is 4, so the square root of 4 is 2. And then what I have left over is the square root of 6. And that's my answer. Number 2, I have a negative square root of 80. So dropping this down, I'm going to put the negative here. And again, square root of 80 is not um, a perfect square number. And what you have to do here is there's actually multiple values that are a perfect square number to give me a product of 80 because you could take 4 times 20 and it gets to be 80. But what you need to do is pick the largest perfect square number because if you took 16 and multiplied it by 5, that is a better option. All right, if you took, actually what I'll do is this. Let's say we did. Actually, let's do this one first and then we'll go back to the other choice. So 16 times 5 gives me 80, but square root of 16 is 4. I got this negative, so I got negative 4 times it by the square root of 5. That's my answer. But some of you guys may realize that, oh, I have 4 times 20. All right, this is an entirely different way to solve the problem. And 4 is a perfect square number. I agree. And if you took the square root of that, I got negative 2 times it by the square root of 20. But here's the thing. You can simplify this further because you can put negative 2 times by the square root, and this could be 4 times 5, So now I have another perfect square number. Square root of 4 is 2. 2 times negative 2 is negative 4. So now I got negative 4 times by the square root of 5. All right, I get the same answer as I did here. It just took more steps. All right, is it wrong to what we did here to start with? No. It just remember that, oh, I'd have to simplify this further. So please keep that in mind. If you look at number 3, I got the square root of 49x cubed. So 49 is a perfect square number because if I take the square root of 49, it's 7, so we're good there. So what I'm going to do is I'm going to break this up into, I want an even exponent, which in this case is 2, times it by x, because x squared times x is x to the third. Square root of 49 was 7, we said. Square root of x squared is x. And what's left over in the radical is just x inside there. So here is my simplified expression for that situation. Here, with the square root of 75 n to the fifth, uh, there is no, let's see here. 75 is not a perfect square number, but if I broke it up as 25 times 3, I would get there. And then this is going to be n to the fourth times it by n. Because n to the fourth times by n is n to the fifth. The 25 and the n to the fourth are what are going to be taken outside of the square root. Square root of 25 is 5. Square root of n to the fourth is going to be n to the second, because remember, you just divide that by 2. And then what's left over inside the radical is 3n. So we also have, so we had the quotient property, which meant that you could break it up into a series of products as a radical. And then there is a quotient property for square roots. In fact, there's a quotient property for any radical. But what they're telling you is this, is you can either make a radical as one big fraction, or you can break it up as to two radicals and simplify it from there. The thing is you have to look at it as a situation by situation basis. You know, do you know if you have to put it as one radical or put it as two radicals? You have to look at that particular situation to see if it's going to help you or not in order to simplify. So in this particular one, it's beneficial to make it as 2 because, oh, 4 is a perfect square number. I can get that out of the radical and write it as the square root of 3 over 2, all right? Because the rule is you're not allowed to have radicals in the denominator, so you're going to have to simplify it from there, okay? So these two are examples to show, all right? It starts out as one radical, but it's beneficial to put them into two because square root of 64 is a perfect square number. Square root of 64 is 8. And so you're left with the square root of 15 all divided by 8. All right, same thing goes for B. Broke it up into two radicals. In this particular instance, both numerator and denominator can get you out of the radical. And so square root of 81 is 9. Square root of x squared is x. And so this is introduction talking about cube root values. So um, looking for perfect cube numbers. So in this particular one here, negative 128 is not a perfect cube value, but in this case, 64, well, negative 64 is, because if you took the cube root of negative 64, you would get negative 4, and cube root of 2 is just left as 2, so that would be your simplified expression from there. Okay, now when you are looking at variables inside the radical, all right, now what you're going to be doing is you're going to be looking for value with the exponent that is divisible by whatever the root is, all right? So In this particular instance, it broke it up as x to the 6 times it by x. The reason for that is 6 is divisible by 3. 6 divided by 3 is 2. That's why I'm able to write x squared on the outside of the radical. Okay? And then what I have left over is the cube root of x on the inside. And again, we'll look at examples to kind of help us through those different processes for sure. And here we have one more. Um, like I said, just take a look at it. If you need to pause it, jot the notes down. Um, but yeah, we will definitely look at problems such as these to kind of give us an idea of how to solve these. So looking at number 5, right off the bat, this is one where you can break it up into two radicals. Square root of 23 divided by the square root of 9. Square root of 9 is 3, so I'm left with square root of 23 divided by 3. I can't do anything else with 23. This is my simplified expression. Same thing goes for 6. I could put negative square root of 17 divided by square root of 100. Well, square root of 100 is 10, so I'm left with square root of 17 all divided by 10. So if I looked at, let's say I looked at 54. So I have the cube root of 54. Because it's cube root now, I have to look for perfect cube values. Okay, so again, look at your list of perfect cube values. But what I can do is I can write this as 27 times 2. 27 is my perfect cube number because the cube root of 27 is 3. So my result is 3 times by the cube root of 2. And that's my simplified expression. If we looked at 12 here, so first thing I'm going to do is I'm going to break this up into the cube root of 25 c to the 7th, d to the 3rd, all divided by the cube root of 64. Now, cube root of 64 can be simplified as 4, so I'm good there. On the top, looking at the numerical value of 25, 25 is not a perfect cube value. There's nothing I could make it as a series of products to make it simplified, so I'm just going to leave it there. So cube root of 25 is going to stay there. But now what I'm going to do is I'm going to look at this c to the 7th. I'm going to break that up into two values. It's going to be c to the 6th times it by c. Reason why I did that is 6 is divisible by 3, and 6 times, c to the 6th times 6, c to the 6th times c to the 1st is c to the 7th. And d to the 3rd is already divisible by 3, so I don't have to break that up, so I just leave it as d to the 3rd. So my simplified expression here will be these two values are going to be taken out of this radical. So 6 divided by 3 is 2, so I got c squared on the outside. 3 divided by 3 is 1, so it's d to the 1st, so I'm just going to write it as d. And what's left over inside the radical of this numerator is 25c, and it's all divided by 4. Okay? All right. So, like I said, when it comes to fractions, you're not allowed to have a radical in the denominator. All right. So, what must you do is what is called rationalizing the denominator. So, I have this 3 square root of 3n in the denominator. Since I can't simplify and get rid of the radical, what we're going to do is this. Because it is a square root, what we're going to do is we're going to multiply both the bottom and the top by the same number. Because if you, in essence, you're just dividing, you're multiplying it by 1. So I'm not changing the size of the problem or anything else. I'm just multiplying both the top and the bottom by the same number. And what that is going to do is the square root of 3n times it by the square root of 3n, it's just going to be 3n. All right, it's going to be the same value. All right, it works for every situation. Square root of 7 times by square root of 7 equals 7. All right, square root of 5x times square root of 5x is just going to equal 5x. All right, if they're the exact same stuff inside that square root and you multiply them together, all the result is just what's inside those two square roots when they're the same. Then you take your top value, multiply that together. 5 times 3 is 15, and I got n, so it's the square root of 15n. And you can have a square root or a radical in the numerator. If you have a situation where it is a cube root in the denominator, what you are now going to do is you're still going to rationalize, but in this case here, you are going to rationalize two numbers. When you multiply them together, it is going to create a perfect cube number. So I had cube root of 9, and the reason why we multiplied this bottom by the cube root of 3, because 9 times 3 is 27, and 27 is a perfect cube number, which allows us to remove that radical from the denominator. And so you do that to the top and the bottom, so then I'm left with 2 times the cube root of 3 on the top, and it's all divided by 3. Okay? So looking at this one here, this one's an interesting situation where you are going to be asked to multiply. You're going to still have to rationalize, but because it's got this subtraction in between them, you are going to multiply both the top and the bottom by what is called the conjugate. Okay, so what the conjugate is basically is you're going to put a 2 and the square root of 3, but because that's minus, you're going to put a plus here. And you're going to do the same thing to this said numerator. So basically what we have on the bottom is a sum and difference pattern. Same number, same number, same number, same number, minus plus. So if you FOIL it out, which you certainly can, what that'll do is you'll cancel out the square roots. But all you're going to do is square 2, which is 4. You're going to multiply square root of 3 times square root of 3, which is the same value, 3. And you're going to put subtraction. All right, just like you would do with the sum and difference pattern. So if you had a plus b times it by a minus b, it's just going to be a squared minus b squared. All right, that's what we got. 2 squared minus square root of 3 squared. That's all that is. On the top, you're going to distribute 7 over 2 plus the square root of 3, which turns into 14 plus 7 times the square root of 3. And 4 minus 3 is 1, so essentially it's just 14 plus 7 times the square root of 3. So if we looked at these examples here, we would have, for the first one, square root of 5 is in the denominator. This one you're just going to take square root of 5 times by square root of 5. Square root of 5 times square root of 5 is 5. And 1 times square root of 5 is square root of 5. So my result is square root of 5 all divided by 5. Looking at 14 here, I'm going to multiply everything by square root of 3 over square root of 3. Square root of 3 times square root of 3 is 3. 10 times 3 is 30, so I got the square root of 30. And thinking about this, let's see, is there any perfect square numbers? 30 divided by 4, no. 30 divided by 9, no. I don't think so. So this is my simplified expression. Here, you're going to be multiplying by square root of 2x, square root of 2x. On the bottom, it's 2x. On the top, it's going to be 7 times it by the square root of 2x because this is on the outside of the radical, and you just multiply them together. Okay? Let's look at 17. So if we look at 17, I would say that I would have it's cube root, but if I took 32 and times it by 2, I'd get 64. So what I'm going to do is I'm going to multiply both the top and the bottom by the cube root of 2. So 32 times 2 is 64, but the cube root of 64 is 4, so I left that on the bottom. On the top, I'm just left with 5 times by the cube root of 2. And I can't simplify that anymore. That is my result. If I looked at example like number 20, here we have square root of 2 plus square root of 7. I have two different square roots. What I'm going to do here is I'm going to multiply both the top and the bottom again by its conjugate. So it's going to be square root of 2 minus the square root of 7, all divided by square root of 2. So it's going to be divided by the same thing, both the top and the bottom. So this on the bottom turns into 2 minus 7. And on the top, it's 12 times by square root of 2 minus 12 times by square root of 7. And the top remains the same, 12 times square root of 2 minus 12 times square root of 7. And 2 minus 7 is negative 5. Final thing that we're going to be taking a look at is adding and subtracting. And the thing about adding and subtracting radicals is you can only combine values that have the exact same stuff inside the radical. So if you notice here that I have a square root of 7 and a square root of 7 for these two terms. What that means is I can combine the 5 and the negative 8. So that is why when I go 5 minus 8, I get negative 3, and I just fill in the square root of 7. You're basically treating these radicals like variables. Because if it was like 5x minus 8x, this is negative 3x. Same thought process. Square root of 11, it doesn't look like the square root of 7, so that doesn't get combined. So my result is square root of 3 times negative 3 times by square root of 7 plus the square root of 11. Okay. Now, looking at this, I have this 10 times the square root of 5 plus the square root of 20. At the moment, they look like they're not the same. So one of two things has to happen. Either I can simplify this, or the problem they gave us is just the simplified expression. All right, normally it's not how the case is, but so what you can do is, again, you can break up 20 as 4 times 5. So now I have this as 10 times the square root of 10 plus 2 times by the square root of 5. So I can take my 10 and add it to 2, which gives me 12, and that is why it's 12 times by the square root of 5. Comes to multiplying, same rules apply. In this case, you're going to distribute here. So you're just going to go square root of 5 times 3, which is 15, minus square root of 5 times square root of 75, which is going to be 5 times 75, which is 375. All right. From here, we have to see if we can simplify. I can't do anything else with that, so I'm just going to leave that alone. But this, I can probably break this up into, um, oh, I can break this up as 25 times 15. So now I get square root of 15 minus 5 times by square root of 15. Now, if you notice, I have the exact same uh, values inside the square root. On the outside is like a 1, and 1 minus 5 is negative 4. So negative 4 times by square root of 15 is my result. All right, we'll do a couple of these, and then, like I said, if you have additional questions, please make comments, and I'm more than happy to work out these problems. So here, I see I have square root of 2 and square root of 2. They're the same, so I can take 3 plus 10, which is 13. So it's 13 times by square root of 2. The only thing that's left over is square root of 6. That's what I have as simplified. That is my result. Looking at these ones, right now square root of 7 and square root of 63 are not the same, but I bet you they can be. So if I wrote it as 4 times by square root of 7, which is already simplified, I got negative 6. I'm going to imagine that 7 is going to be one of the values, and it's 9 times 7. Thankfully, 9 is a perfect square number, so 4 times by square root of 7. Square root of 9 is 3, but 6 times 3 is 18, so now I have square root of 7 here. Now I have the exact same stuff. I can take 4 minus 18, which gives me negative 14 times by square root of 7. And that is being able to look at properties of radicals. Hope this helps. Until next time.